All right, extraction of buildings. So moving from the DTMs that we were just talking about and creating that, this is now a feature extraction of a surface feature. Now, what is really interesting about buildings is that it only has one return except for the edges, right? So if we were to look at a building, we see that the building itself, the roof of it, won't have a lot of echoes, right? Because you have a rooftop and it's going to have a single echo that's returned. So a lot of the times the buildings end up becoming part of the ground, and that's why the DTM construction process needs to have that change in elevation or the change in height that it's identifying and saying, okay, here's the threshold. Anything exceeds this, it is no longer a part of the ground. So this is one of those features that we can use to be able to identify buildings. So when we are dealing with buildings, we also have some other challenges that come with it as well. So we have other objects, such as trees, that can cause problems, especially around houses. So I've seen some really neat projects in the past where you have a house that has a ton of trees, and the project was to try to determine if that house would be optimal for a solar panel. So you have these little tiny buildings with like really small roofs, and then you have these great big, like, 60-year-old trees that are overlapping that house. How can you actually identify where the roof is to be able to measure it and get like the sun's angle on it? So the trees are a big deal. You can also have other features like power poles. There's like radio towers. Some people put towers up in their yards. That can also cause an issue with extracting your buildings. So there's lots of stuff that does happen in people's yards, but trees are the biggest one. So there are different ways that we can try to extract those buildings from underneath those trees, or even just extract the buildings from a DEM that is clean without any trees overlapping. One of them is the height, so I was talking about that. Another one is texture. So again, a building has a very clean echo, so the intensity tends to be a little bit higher, so we're not going to see as much diffuse scattering from the laser point. We also have the one returned echo, which is what I was talking about earlier, and also higher point densities we can use. So if we slow down over that area, or we apply a pulse repetition frequency, or we do multiple passes over the area where we're looking at buildings and trying to extract those buildings, we can have a better possibility of doing shapes. And so if we have a lot of points, we can say, okay, anything that has 90-degree angles in it is probably not a tree. It is most likely part of the building, especially when it comes to the horizontal. So I don't know many trees that have exactly 90 degrees with nothing coming off of it, right? So that shape constraints is really helpful. This can be challenging if you have a round building, of course, or a triangle building, I guess, would not be 90 degrees, but we could still create a triangle out of that. So shape constraints, if we are dealing with circular buildings, we have to apply a circle. But again, some trees are very circular, and they might be a little bit fuzzy, but they can have like a very nice circular shape. So again, can be a challenge to work with. We can use amplitude. So again, because it's like if you have like a flat roof, it's going to come back very strong. The pulse width can also help differentiate. So when we have a sloped roof, the pulse that the beam width actually like elongates along that rooftop, like along the slope. So we can actually measure that pulse width with like a full waveform Lidar, rather than just the time of flight. We can also look at it in terms of the horizontal versus the vertical as well. So that's another way of identifying it. Trees, it's going to be broken up into a lot of little pieces, right? You're going to have a lot of little returns rather than one big long return. And another way that we can also try to extract buildings is using multispectral data. So bringing in that satellite imagery or aerial photography. But you don't necessarily have to have that separate component, because if you do have high point densities and you have multiple returns, you can generally get your buildings out of that. Because multispectral data cannot see through trees, right? We were aware of that, except for like microwaves, but if you're going to add microwaves into LiDAR, you are adding a whole new level of complexity onto a project that doesn't really need it. So just keep your high point densities and do multiple returns, and generally you'll be able to find the building that you need to. So we can segment our data based on areas. We can just like segmented regions, so we can like block out an area saying that these are the types of buildings that we're looking at. We can use neighborhoods, which are also similar idea. Block out like a neighborhood and saying this is the type of trees that we're going to expect in this area. And we can also use local regions, so we can really zoom in, like for example, a school park. We can go in there and try to like just identify that one building that's in that area. We can also do classification. So if we do a supervised classification with our LiDAR, which you can do, you don't necessarily just need to do it with like regular remote sensing data. You can apply a supervised classification, and that increases the reliability. So you go out, you can collect field data, and you can be like, these types of points are going to be this part of this type of land feature. These type of points are going to show these, and you can create a supervised classification with LiDAR. So that really increases the reliability of your final result in finding those building extractions. So we have a major step to begin with for building extraction, and that's outlining our building footprints. So this is what you guys are doing with your digitizing. And so there is a few steps that need to happen. First, you need to detect the pixels and or points that make up the outline and form a polygon of the building. So which points are the outline of the building? And that sometimes is challenging. If you were to follow every single point along there, it's going to create some really strange looking buildings. Also figuring out which one is the corner of the building. How do you determine that corner? So, and which points are part of the building, which points are part of something else, right? So really watch that as you're going through. You may have to change the surface that you were working with. And I'll show you guys how to do that I will have shown you guys how to do that by the time you're here. Then we're going to reduce our points, so only relevant edges are preserved, right? So we're going to help ourselves with generalization. Do we want to see every single point all the way along, like we would with a tin in a gift wrap algorithm, or it's like bouncing back and forth? Or do we want to say, you know what, we only need from corner to corner, and we're going to draw that along there? Of course, it depends on what you're using LiDAR for. Sometimes you do want to preserve that tiny bit of information. So again, it comes down to the scope of your project. Then we have a fantastic way to identify our buildings and to draw them out. One constraint is known as parallelism, and the other one is known as rectangularism. So both of these identify our buildings. So parallelism means anything that's across from each other is straight lines. Everything that, and that will say, okay, you know, one side of the building needs to be parallel to the other side of the building, which should make sense, especially like big commercial buildings, and even houses, right? Even if it's a fancy, like put together house, it's still going to have some element of parallelism that's included in it. Rectangularism means it's going to have 90-degree angles. Now, of course, if you have a triangle building, you're not going to have that. If you have a round building, this is going to be a challenge here. So that those constraints can cause problems. So it does require you to go back in and try to analyze what you've done. So my suggestion for you with the LiDAR is to follow rectangularism and follow parallelism. So there are manual versus automatic methods. We generally use ransack because we use like sampling points and then we create a polygon from that. So that would be the initial extraction, then you would go back in and manually adjust it as you needed to. Our challenges, as I've been talking about, generalization, what points do I need to use along the edge of the building? Outlier preservation, do we keep certain points that seem to be a part of the building but don't really follow the shape of the building? If you don't have any field validation, then how do you decide on that? Next thing is the curved versus rectangular buildings. Well, that's a big deal, right? Trying to figure that out. And then exaggerated outlines as well. So because we have multiple returns on some of the edges, do the edges actually become bigger than what they really are? So here's an example of building extraction. We're trying to find these points. We're trying to figure out what's part of the building versus not. You can see how the trees are being included in the exact same height. So we have returns. We have this big tree, right, that's overlapping in the middle of this building. So we got to figure out what is actually part of the building and what is not. So we come over here. We started putting in the rectangularism and parallelism constraints. So we can see that we're starting to create 90 degrees. We're trying to identify where those edges are. And then in here, it's still showing that this tree is a part of it. So, you know, how do we classify based on the possibility that it's the building outline? And then it's just showing kind of like the initial starting point of the area that we're looking at. This is known as a local segmentation, so we're looking specifically at one area. So that's this is some of the challenges. So this is what we're aiming for, is this building footprint here. But some of these, depending on the information that we're given and how we're going to identify between the tree versus the building, do we keep the tree, do we not? Depends on your application. So step 2 is building reconstruction itself. So this is actually creating what it looks like. So we have geometric modeling, we have something called formal grammars, and we have something called systems. So all of these different models are automated methods of trying to recognize what a building should be. This is like making it pop out of the ground and creating a side. Now, if you were to do Lidar, you're not going to see the side of the building, or very little of the side of the building. If you did terrestrial, this is really where you're going to like extract out that. So combining Lidar with terrestrial laser scanning is really powerful, because you can get rooftops that you didn't have before. You're going to get that multiple return information with the Lidar. And then if you include the terrestrial laser scanning, you're going to have all of that detail. So it's really, really beneficial to do that. And we refer to this as object recognition. So geometric modeling, this is building from the boundaries. It's called constructive solid geometry if you do it in CAD. And so you're kind of pulling out that building, and you're going to create that building, and you're going to be able to like draw the whole thing in 3D. Formal grammars and procedural models, this is a really complicated program of algorithms where you have variables and symbols, and you have some rules that you set within the algorithm, and then it'll automatically pull it out. Again, this works really well in software that allows for modeling of algorithms. And then so then it works with raster or vector, so you can use either with that one. And then there's other systems that you can use. So the actual systems themselves can be manual. You can manually draw it. Semi-automatic, which allows, and then the automatic, which can include these two if you need to. So there are still a few issues in building recognition. So we talked about like the issues of trying to extract the footprint, but just the building recognition itself, we have problems. So topological correctness can be a problem. This is where, you know, are your lines actually connecting together? Do you have gaps? And of course, when you're dealing with points, do you have intersections that are happening? Like, what's happening in your topology? Do you actually create a polygon? Then we have the nonlinearity of constraint equations. So if we're trying to automate this, we're dealing with nonlinear equations. And that is why a lot of software doesn't actually do this as like just an automated process, because it's too hard. And you may end up with a diverging solution rather than a converging solution. We also have network constraints. So we have our data, we have like as much as we can working amongst like all the different points. So we can only capture so much automatically of what is out there in the real world. So trying to bring that in to a point cloud, and then trying to automate lines from that point cloud that actually makes sense. There's only so much we can do, and the computer can do at this time. Maybe in the future everything will be automated and and that will be great because we have AI and everything's learning and deep learning and all of that other stuff is happening. So maybe this might improve, but it's still partly an issue because our buildings are not always the same. So our networks are never the same. Then we have also a problem of primitive models. So this is like our very beginning starting point at like, okay, we want our building to look like this. So if we were to say that architects made buildings all exactly the same, then this would be great and it would be very powerful. But they're very, very weak to start off with because like we say this rectangle is what a building is supposed to look like. This rectangularism and this parallelism are my constraints. So this is what the model is going to look like. So now extract that. And so because it's such a weak start that anything complex becomes too difficult for our software to be able to recognize. And the last but not least is the generalization issue. All the way through every kind of map that we do, every type of remote sensing that we do, generalization is an issue. How much of the building do I really want to show? And how much is my Lidar actually allowing me to show it? So there's a few lessons that has been learned over the years in building reconstruction. So these are just some of the lessons, things that keep in mind as you're trying to rebuild a building. So there's assumptions in parameters and weights that really it shows that the building is not derived in a systematic manner. So we have to put in all these assumptions before we can actually automatically control what's in the algorithm. Then we have reliability. So it's still not really high. Automated processes, we can't fully rely on them because of so many different exceptions. There's always exceptions to every rule, and computers don't handle exceptions very well because they need to really learn. That's why like Tesla cars have all those cameras, and they still they capture thousands of hours from their vehicles to be able to automate the driving, but we still can't rely on it, right? Because it's still not very high enough to be able to say, yes, it's fully reliable in every situation. Most of our buildings are created using heuristics, which is the trial and error, or guessing as to where those buildings are. We're guessing at the footprints when it comes to Lidar. We also can use data fusion, but that it still has deficiencies. So we're still looking at scale issues. Scale issues is the biggest thing. You can sit there and try to match it all up and be like, this is where it is, but you're going to see things that are offset. And that is... that's going to be challenging for you. The next thing is weighting in data fusion as well. So do I rely on my photogrammetry data more than my Lidar? Which one is actually more accurate? Which one actually makes more sense? What if I bring in satellite data? Is that better? Which one is more reliable? Which one is supposed to have more weight, right? So how do I bring that all in and color the point clouds? That's still a very complex question to ask because every situation is different. Then there's also thresholds, and you're going to spend, if you try to use an automated method, you're going to spend a lot of time setting up thresholds. Once it meets this, then stop. Once it meets this, then stop. Once it meets this, then stop. So those thresholds are assumed. A lot of them are assumed. Some of them can be calculated, but you're going to spend a lot of time setting that up. You also need to know the scope of your project. And as much as we sit there and say, yeah, this is one of the hardest things to stick to, really. And you're going to find that with your capstone projects. You probably already have gone out of scope. And really it's just because of the fact that something might come up in the project and you're like, oh, we need to dive into that. Oh, this comes up, so we need to figure this out. Oh, this comes up, we need to figure this out. At what point do you just generalize and say, you know what? This error is going to be an error in the project. And I'm just going to identify it and say this is what happened, right? So you really got to focus on that scope. The other thing is things are changing constantly. When do we update our data? How much is that going to cost? Who is going to update it? Why are we updating it? Do we need to go back and change it? Like you look at Northwest Calgary, for example, or even SAIT. Like we take the data that the laser scan data that I have given you. Well, we've already removed a building. There's things that have changed as well outside of that. Like what about the trees? The trees have changed. So at what point Do I update that? And why do I need to update that? So the last thing too is systematic evaluation. So you need to find a way for every single project that you do to go through and evaluate it piece by piece by piece. Because otherwise, if you don't evaluate all the way through, you're going to lose some of your accuracy, you're going to lose precision, you're going to lose your reliability, and then you come to validate it at the end and it's not going to look like what it should. So you need to be evaluating all the way through. So that is all of the feature extraction stuff. So part 1 is the other video that I did. This is part 2. So make sure you review both of them. The forestry component we're going to kind of bring in a little bit into our projects. So make sure you read up on that as well. And then next week we're going to look at Lidar quality control, and then that will be the second last of our lectures. So I look forward to seeing you next week.